Arithmetic, addition, subtraction, multiplication, division, review. Definition: mathematics. There is no generally accepted definition. Mathematics comes from the Greek mathemata, meaning knowledge, study, learning. Definition: number. A number is a mathematical object used to count, measure, and label. So far, we have covered counting and labeling. We took a bunch of apples and lined them up. Then, used counting to label the total amount of apples. The only reason we can do this is because we see similarities among the differences. As an example, I want you to count the objects in this following picture. Go ahead and tell me in the comments how many things you counted. Note, I am not asking you to count all the apples or chairs, both of which are groups of different looking things that we humans have classified as apples and chairs based on an objectively observable feature, attribute, or characteristic. I merely ask that you count the things, a concept that states that objects exist, objects which are distinguished from other objects. The issue with this image is that it's not possible to distinguish anything from anything. You cannot count the objects if you can't see objects. Counting and labeling quantities only make sense when you have units of a concept. It is because of the concepts or units that we need numbers. So the concept of apples allows us to group different objects into one unit. Then the size of that group is simplified into a number. We lined them up and then counted them. After each has been counted, the total number is the last number given. And this is how we label the number of objects in a group. For example, we would start here with 1 apple, 2 apple, 3 apple, 4 apple, 5 apple, 6. We have 6 apples in total. If we remove the apples, but we keep the numbers, we could use this order of numbers to count any other concept, but it must be some concept. Smaller numbers to the left, and then grow by 1 the more right you move along it. The number system we use is called the decimal numeral system, or base 10 positional numeral system. All the numbers in the decimal system can be abstractly reduced to the form a over 10 to the power n, where a is an integer and n is a non-negative integer. As an example of that, 7 can be written as 7 over 10 to the power 0. Anything to the power 0 becomes 1, so this becomes 7 over 1, which is 7. We can also use 50. 50 could be, say, 500 over 10 to the power 1, which would be 500 over 10, which would get us 50. Part of the decimal system is the fact that we can go in the opposite direction. And we can have examples like 0.5, which would be 5 over 10 to the power 1, which is 5 over 10, which is 0.5. Or 0.05, which would be 5 over 10 to the power 2. 10 to the power 2 is 100, so it's 5 over 100, which is equal to 0.05. So in the decimal system, we can write any number in the form a over 10 to the power n. The radix of a number system is the number of unique digits to that system. Decimal uses 10 unique digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All the other numbers are a combination of these 10 digits, having the number furthest left representing the highest value, and the furthest right representing the lowest value, such that in 1234, the 1 is actually representing a value greater than 2, 3, or 4. It represents the 1000th place. So the 2 actually represents a number greater than 3 or 4. It is the 200. The 3 is 30, and the 4 is just 4. So altogether you get 1,000 plus 200 plus 30 plus 4. 1,234. Let's do some quick examples. Which number is greater? A, we have 582 or 589. Looking at the number order, we have 5, 5, that's the same. 8, 8, that's the same. 2, 9. 9 is higher than 2, that one wins. In B, 3,576 or 3,476. Following the order again, we can see 3,000, 3,000. This would be 500, this would be 400. 500 is greater than 400. C, we can see here we got 5,000, 5,000. 700, 700. 50, 40. So 50 is greater than 40. 792 or 6,082. If we look here at this part, we have 7, which is greater than 0, but there's one place value higher here, which technically there's a 0 there. 6,000 is greater than 700. E, 4,110 or 4,101. 4,000, 4,000. 100, 100. 10, 0. 10 is greater than 0. Last one. F, 8,192 or 8,291. Following the order again, we have 8,000, 8,000. 100, 200. 200 is greater than 100. Reviewing addition and subtraction. Addition is the idea that since objects are similar enough to all share a name, like chairs, bears, and fruits, then taking in more than one of those objects will increase the number given to the total. Since we use a decimal system, we have to be careful how we add in arithmetic. In real life, adding apples to a pile of apples is done by taking an apple and putting it on top of the pile. Arithmetic, with the base 10 system, as we said in the addition video, moves up a number line one at a time. But how do we know what that number is without memorizing each and every number? The decimal system requires you only remember 10 numbers. 0, meaning the absence of an object, like after you have eaten all of your apples. Then it increases by 1 until you reach 9, such that you have 0 plus 1, which equals 1. You take that number and you start over. 1 plus 1 equals 2. 2 plus 1 equals 3. 3 plus 1 equals 4. 4 plus 1 equals 5. 5 plus 1 equals 6. 6 plus 1 equals 7. 7 plus 1 equals 8. 8 plus 1 equals 9. But 9 plus 1, what do we do there? We could continue to just randomly add certain symbols to our number line, such that we say it's this. But that would just mean that we'd have to remember an infinite amount of numbers. Instead, it's a lot easier to repeat those numbers while adding a 1 in front of each one of those, such that 9 plus 1 is 10, a 0 with a 1 in front of it. Once this pile runs out, you move up. 1 plus 1 would be 2, so 19 becomes 20. You can think of it as the 9 rolling over to a 0, and the second place value begins to count. The first place pattern repeats the same as before, and then so does the second. Therefore, we can see that the second place value only changes after 10 digits have passed in the first place value, and thus is called the 10-place value. The first is the 1-place value. Subtraction also must account for this decimal system. Let's do some examples. Robert drives a truck. On Monday, he left Prince George to drive 1,639 kilometers to Whitehorse. On Wednesday, he left to drive 1,222 kilometers to Inuvik. On Saturday, he left to drive 3,149 kilometers to Yellowknife. How far did Robert travel altogether? Since the unit, kilometer, doesn't change, we can add. Since we can add all these numbers together, we can just ignore the unit and just use 1639 plus 1222 plus 3149. So then, what does 1,639 plus 1,222 plus 3,149 equal? Let's start with the first two numbers. We have 1,639 plus 1,222. First thing we must do is add together the numbers in the first place value. 9 plus 2, which is 9 plus 1 plus 1, which is 10 plus 1, 11. If we put an 11 down here, we can see that this 1 has gone to the 10 place. So it's actually better to write it with a 1 here and carry the 1 up here. Now it's time to add the tens together. That's 3 plus 2 plus 1, which is 3 plus 3, which is 6. Now we can add together the 100 place values. 6 plus 2, 8. Finally, the 1,000 place values. 1 plus 1 equals 2. So now we've got 2,861. 2861 plus 3149. Again, starting with the 1 places, we get 9 plus 1, which means we have to roll over and get a 10. If we put the 1 here, we're going to have to make sure that we add it when we do this next column, such that we get 6 plus 4 plus 1. Which is 6 plus 5, which is 11. So let's fix this. Put a 1 here, 1 there, and that 1 carries. Now we have to deal with the 100 column, which is 1 plus 8 plus 1. Which is 9 plus 1, which is 10. So again, we have to carry over. Finally, we got 1 plus 2 plus 3, which we saw before, gives us 6. So, altogether then, Robert had to travel 6,010 kilometers. Returning the units so that we understand what we're talking about, because the whole point of addition requires concepts. Example 2. At the beginning of the month, Anne had $2,340 in her bank account. Anne deposited $936 one day and $94 another day. Anne took out $790 the next week. How much did Anne have in her account at the end of the month? Anne starts out with $2,340 and adds $936 and then adds $94. So, 2,340 plus 936 plus 94. And then takes out $790. So, we now have 2,340 plus 936 plus 94 minus 790. So, let's do the math again. 2340 plus 936. 6 plus 0, 6. 4 plus 3, 7. 9 plus 3. Let's write that one up. 9 plus 3. That is 9 plus 1. So we have to roll over plus 2. So we'd get 10 plus 2, 12. So carry the 1. 1 plus 2, 3. Okay, take that 3,276. Add 94. 6 plus 4. Let's look at here. 6 plus 4 is, let's go 6 plus 3 plus 1, 9 plus 1. 6 plus 4 means 10. We have to roll over. Carry the 1. Now let's do the tens place. 9 plus 1 plus 7. So we got 10 plus 7. 17. 7 here. Carry the 1. 2 plus 1. 3. 3 plus nothing. 3. Finally, we have 3,370 minus 790. Subtracting is a bit of a new ball game. 0 minus 0, that one's easy. 0 minus 0 is 0. But now we have in the tens column 7 minus 9. How can 7 minus 9 give you a real number? Abstractly, it can give you minus 2, but that doesn't so much help us right now. Well, if we recall how this works, we know that the other numbers remaining, say the 337, is actually 336 plus 1, which can be 335 plus 2, or 334 plus 3, and so on, until you get 328 plus 9. So now, you could say that there's actually 328 plus 9 minus 9. The remaining total would have to be 328. So we could see if we had 3370 over 790, that's 0, but this is actually 328 plus 9 minus 79. So those 9s now cancel. However, that method is very messy. So it's a lot easier to do it like this. Zero minus 0, 0. 7 minus 9, not possible. So borrow, since this is actually 37, let's borrow a 10. 10 plus 20 plus 7. Give this 10 to that 7. So he becomes a 2, and he becomes 17. So now we have instead 17 minus 9, which would give us 8. We then repeat the process, having 2 minus 7 is actually 32 minus 7. So let's just borrow one of the numbers rather than the whole 30, reducing this to a 20 and giving this a 10. So now we have 12 minus 7, which is 5. So we have a 5 now. And 2 minus 0, which is 2. So therefore, Anne has $2,580 in her bank at the end of the month. Multiplication and division review. Multiplication and division, as we discussed in those videos, are based around groups of different concepts, which are related by some relationship which is quantifiable. For example, there are multiple eggs in a carton. 12 to be exact. The relationship between eggs and cartons is 12 eggs, called a dozen, goes into one carton. Therefore, 5 cartons would be 5 sets of 12. But what is 12 plus 12 plus 12 plus 12 plus 12? Since multiplication reduces to addition, we need to be cautious of the place values, such that in this case we have 12 eggs times 5 cartons. In order to do this, we first go 5 times 2. 2 or 2 times 5. It's the same thing. Which is either 5 groups of 2 or it's 2 groups of 5. 2, 4, 6, 8, 10. 5 plus 5, 10. 10 equals 10, so it works either way. 10. Just like before, we have to put that 1 at the top, called carrying the 1. In multiplication, we have to go this 5 times 1, and then plus this 1. So we'd have 5 times 1 plus 1, which is 5 plus 1, which is 6. So 12 times 5 equals 60. So we'd have 60 eggs. Why does the 5 interact with the second place value in multiplication, but not addition? In multiplication, we have 12 times 5, which is 12 plus 12 plus 12 plus 12 plus 12, or 5 plus 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 5. Looking at it in this form, we can break it into a set of blue and a set of red. The blue set will have 10 groups, and the red set will have 2 groups. Therefore, if we still wanted to add up a total of how many we have, if we separate the red from the blue, we would get 10 groups of 5 eggs each, which is 50 eggs, plus 2 groups of 5 eggs, which is 10 eggs, which is 50 plus 10, 60. So in multiplication, the red set is the ones place, and the blue set is the tens place, but they both have to interact with that group of 5. Whereas if you had 12 plus 5, that is 10 plus 2 plus 5. The tens place and the ones place. You can see then that the 5 only interacts with the 2 in the ones place and has no interaction with the 10. Let's do some examples. There are 8 cereal bars in a box. A. How many bars are in 2 boxes? B. How many bars are in 4 boxes? C. How many bars are in 8 boxes? D. How can you use one answer to get to the next? With A, we have 8 times 2, which is the same as 8 plus 8, which is 16. B is 8 times 4, which is 4 groups of 8. 8 plus 8 plus 8 plus 8, 32. C, 8 times 8. That is 8 groups of 8. 8 plus 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 8. That is 64. D. How can we use one answer to get to the next? Well, we can note that in A, 8 times 2 is 8 plus 8, which is 16. In B, we have 8 times 4, which is 8 times 2 plus 8 times 2, which is 16 plus 16. 16 plus 16 is 32. In C, we have 8 times 8, which is 8 times 4 plus 8 times 4, so 32 plus 32, which is 64. This method can simplify our addition. Example 2. There are 9 marbles in each bag. Alice wants to buy 54 marbles. How many bags does Alice need to buy? What we have to know from this question is that Alice wants a total of 54 marbles. Those 54 marbles are divided into 9 marbles per bag. So we can write 54 divided by 9. Or we can write it as 54 over 9. Dividing is a bit of a different game from multiplying. Since Alice cannot yet buy them, she's going to have to imagine. But she can imagine removing 9 marbles from a bag and then counting 1 bag each time she does. So let's do that. So we'd start with 54, and we would remove 9 marbles from that imaginary bag, and we'd get 45 marbles remaining. And we call that 1 bag. Then we'd have 45 minus 9, and that's bag 2. At 2 bags. This is equal to 36. So 36, and so on and so on. We'd get something like this. 54 minus 9, 1 bag. 45 minus 9, 2 bags. 36 minus 9, that'd be 3 bags. 27 minus 9, 4 bags. 18 minus 9, 5 bags. 9 minus 9, we're at 6 bags. 9 minus 9 is 0, so we're done. So 1 plus 1 plus 1 plus 1 plus 1 plus 1, 6 bags. So Alice would need to buy 6 bags of marbles if each bag contains 9 in order to get to a total of 54. Alternatively, division can be written like this. It starts by asking yourself, how many times does 9 fit into 5? In this case, the answer is 0. So we write a 0 there. Then the question becomes, how many times does 9 fit into 54? And we'd have to go 9, that's 1. 9 plus 9, that's 2. That gets us 18. Plus 9 gets us 3. That gets us 27. Plus 9, so we're up to 4. And that equals 36. So we can still fit 36 into 54, so let's keep adding. One more 9. We're up to 5 9s. 36 plus 9, that's 45. Plus another 9, we're up to 6. And that would be a total of 54. You can't, if we add another set of 9, that would be over 54. And so we stop. We stop at 6 bags. This alternative form works a lot better when you have a lot of numbers and a small number. Like questions like this, when you want to know what is 1/2 of 57,826. Doing an example like this, we ask ourselves, how many times does 2 fit into 5? Well, it would fit in twice, because that would be 4. If we did 3, that would be 6, and that would be too much. That leaves us with 1. So instead of now asking how many times does 2 go into 57, we need to know how many times does 2 go into 17. We know that 8 plus 8 is 16, so that's 2 sets of 8. So 2 times 8, 16. That also leaves us with a 1. Let's carry this 8 all the way down. What is 18 divided in half? 9. That leaves 0 behind. So then it becomes just a 2. How many times does 2 fit into 2? Once. It's a 2. It's another 0. And then finally, bring down the 6. How many times does 2 fit into 6? 3 times. 6. 0. Therefore, 57,826 divided in half equals 28,913. And that is the end of our review on arithmetic, addition, subtraction, multiplication, and division. In the next video, we will cover exponents. Don't forget to subscribe to the channel and like the video. See you next time.